Hello. A few days ago, I presented this workshop at a conference called DevWorld in Melbourne, Australia. The audience for that workshop was primarily iOS programmers, most of whom had never done any Rust before. And in that, we went through how to create a Rust library, how to compile it for iOS targets, how to bring that into an Xcode project, and then had a look at sending data back and forth between Rust and Swift over the C-based FFI. So the bulk of that workshop was this written tutorial which I put on GitHub. If you are interested in doing this for yourself, I've put a link to this in the description and you can sort of work through the instructions at your own pace. What I want to do in this video is basically run through this entire thing as a demo, including one or two of the exercises, and also I'll include some of the slides that I presented in the workshop itself to provide a bit of motivation and context for why you would want to do this in the first place. So let's do that for a start. Traditionally, if you were going to do a cross-platform app, say for iOS and Android, and you had some back-end code that you wanted to share between those apps, you would probably be using C++. It was one of the most logical choices that you could compile down to something that's compatible with both platforms. And back in the day, this is how you might have integrated it into iOS. You would turn it into a static library combined with a header file, a C-based interface, or C++ based interface even, and then link it with Objective-C. And Objective-C++ allows you to call into C++ code directly. So before Swift came along, this was pretty attractive. But these days we like to use Swift, and so far Swift doesn't support C++ and isn't going to in the foreseeable future. However, it does have excellent support for C bindings, standard C bindings. So if you want to write your cross-platform code in C++ still, that's totally fine, but you have to hide all the complexities of C++ behind a straight C interface, a C formatted header file. And then you can compile that into a static library, a header file explaining what functions are present, and you can link that into your Swift binary, either directly into your application or as a framework that you maybe wrap with some Swift wrapper functions and then use in your Swift application. So what we're proposing to do today is to get rid of the C++ part and replace it with Rust. Everything else here will stay the same. But, why would you do that? Everybody already knows C++, right? Or claims to know C++. You read about all these good things about Rust on Hacker News, so it must be good, right? Also, they have a really cute mascot called Ferris. No, it turns out there are actually some good reasons to use Rust, apart from C++. Let me move myself out of the way there. If you're familiar with Rust, these will be familiar to you, but I'll summarize it really quickly. It's really fast. There's no garbage collection, so you don't get those unexpected slowdowns when it's cleaning up memory. They aim for zero cost abstractions in the standard library, which means that basically you don't pay at runtime for nice syntax. Memory safety is my favorite one. You can't have different pieces of code or different threads writing concurrently to the same piece of memory, not without some sort of synchronization that the compiler can prove. So that means that all these things that used to cause crashes or security bugs in C++ code, like use after free, double free, null dereference, all these sorts of things can be enforced as safe by the compiler at compile time, which is awesome. And of course there's the ecosystem as well, which is a lot more modern and nice than C++. You get the crates, which are like NPM, and a community that uses standardized tooling for everything from dependency management to the build system to how even to format your code automatically. So it's really quite cool. Are there reasons to maybe not use Rust? Yeah, these are the two main downsides that I've found so far. One is that it's quite a steep learning curve. If, like me, you're used to solving your problems with object-oriented programming languages that allow lots of mutable state, there are certain things in Swift that we do all the time, like delegates, for example, that are simply not allowed in Rust, or they're simply impractical in Rust because they just rely on this shared mutable state to work in any ergonomic manner. So I've not only been learning how to use Rust, but I've also been learning how to re-express my problems in a way that I can write them in Rust. And also the compiler is kind of slow. I mean, they're working on it all the time. I don't want to rag on them, but it's the truth that at the moment more complex projects are pretty slow to compile. So, in the first module of this, we're going to be building a library. So a standard Rust binary, when you generate one with cargo, looks like this. You have a main file inside a source file. Library is quite similar. You get a lib.rs inside a source folder, and there's slightly different contents in the cargo.toml. What we're going to build in the first module is actually a library with an example binary contained inside it, which is something that you can use to test the library and show people how to use it. It's just a convenient way for us to make sure that our library is doing what we want to before we get all the way to embedding it in Xcode. And in terms of what we're actually outputting, we're going to set up our cargo.toml to output a standard Rust library and also a C-style static library, which we'll see in our target folder when we go looking for it. I think that's all the slides I had for this one. Yeah, okay, let's go to the setup instructions first, just to make sure that we are on the same page for everything. So, we need to make sure that we have Xcode installed. I have Xcode installed, that's fine. We need to make sure that we have the Xcode command line tools installed, or Rust doesn't work. They're already installed here. We also need to make sure that we have the path for the Xcode command line tool set to the actual location of our Xcode folder. I already have Rust installed. I already have the extra Rust features installed. I can sort of show you. I've got a few bits and pieces going on here, but the active toolchain is stable, 1.37, and for this toolchain I have the ARM64 Apple iOS target and also the x86-64 Apple iOS target for running on the Apple simulator, iOS simulator. So I'm going to skip over the basic test because I know that everything's working. Let's get on with the actual workshop. So first thing we're going to do is create a static library, which we're going to call Anvil, which is a bit of an in-joke from the conference. Cargo new lib Anvil. Brilliant. Okay, now we want to edit this, so let's open this in Visual Studio Code. That will be good. What's it say? Open cargo.toml, add a lib section. All right. Lib crate type lib static lib. So those are the two types that I was talking about before. Now I'm going to edit this and delete the generated test. And I'm going to declare a function which is hello dev world, because that is the conference that this is from. So there's a couple of things to see here which I didn't actually explain in the text. No mangle means that we're not going to mangle our name to include the C++ style codes about what the parameter types are and the return type are. And all it's going to do is print a function. So let's go ahead and build that from inside the actual project. Good, it builds. And inside the target debug folder, we should see those outputs that we were looking for, the static library, the Rust library, and so on. We can also use the nm tool to inspect the symbols that are being exported by our object file. And we can see that hello dev world function is actually present, which means we should be able to use it from C or from Swift. So now we'll go ahead and make our example application, which will allow us to actually call this from Rust code and make sure that it does actually print something to screen. Testanvil.rs. Alright. Come back here, Visual Studio Code. We're going to use you to edit testanvil.rs, and we'll just bring in all our library functions using the use and call hello dev world in our main. And this is something that we can just run semi-automatically using cargo because it knows what examples are. Okay, and it's run our function as expected. So we haven't done any iOS yet, but we've got our library there with the static library type. It's producing a .a file, which is the main things that we want to get right in this early stage. There was a bit of an exercise there, which many people chose to do, just using a crate. We'll use a crate later, that's fine. I'm not going to bother demonstrating how to do it from C. That's something else you can try if you want to. So, did I have any slides for the next section? Yes. Alright. So, to bring this into Xcode, we have to supply both the static library, the .a file, which we were looking at just a moment ago, and also a header file, which contains a list of function prototypes for all the functions which we've exported, so that Swift actually knows how to call them. That information is not present in the static library.a file. We're going to do two cross compilations, one for ARM64 and one for x86-64. So that covers the physical device and the simulator. And that will produce two different files called libanvil.a in different parts of the target subdirectory. To make this easier to handle, we're going to merge them into a single library called libanvil.a. When it contains multiple architectures like this, they call it a fat library. That's why the tool's called lipo. This is terrible. I blame Apple. Anyway, okay, that's the main thing for this section. So let's go back to the instructions and go through this one. Let's have a go at section 2. In this one, we're going to start building our Rust library for different platforms, which we can do by passing the -- target option to cargo just inside our build folder. So we'll build one for ARM64, another one for x86 simulator. And now we can use that lipo tool, which I mentioned, to inspect these output files. You can see these are all organized into their own folders under the target subdirectory, one for the ARM64, another one for the 64-bit x86, and then under debug versus release. And they're both called libanvil.a. One of them's got this architecture, one of them's got that architecture. Now we can use this other command, lipo create, to combine two of them into a single file. And if I use the info command again, we can see the architectures are in a fat file, x86, 64, ARM64. Brilliant. So we have our .a file, which contains both of these, and Xcode knows how to use this. It can pluck out the correct architecture for whichever type of phone we're building for at the time. So we're now ready to actually use this in an Xcode project. We don't have the header file yet, but we're just going to make that up by ourselves in the first instance. So let's fire up Xcode, new Xcode project. Ooh, that's a bit too big. Single view application for iOS, Anvil tester. That's me. That's good. Right, let's make this a bit smaller so we can see what's going on. Alright, what do I have to do with this? I'm going to make a new group just to keep this tidy for my Anvil library. I'm going to call it Anvil. And now inside that I'm going to create an anvil.c file, which I don't actually need, but it will, by creating a C file, it will automatically create a header file for me and also ask me about bridging headers, which is something that I do want. So we're going to create this inside that group folder, and this is important. It's going to ask me if I want to create an Objective-C bridging header. And this is a header file, a .h file, where I can include any C headers that I want to expose to Swift, and then they'll be available inside my Swift module. So I'm going to, having done that, delete anvil.c because I don't actually need to supply any C code. But I do need the header file, and I do need this bridging header. So I've done that, and now inside our manually created anvil.h, I'm going to declare this particular function, which is going to be exported from our Rust library, hello dev world. And then to make this available to Swift, I'm going to include anvil.h in here. Now I need to bring in the actual library. Okay, I'm going to go into my Rust project, target. Here's the one that we created earlier, and I'm going to drag that into the Anvil group. Let's just copy it in for now and add it to our main app target. So in this case, that is there. And if we look at the project settings, what we should see, this is a bit hard to see, it's actually automatically added it as a linked library because we dragged it into the project like this. So make sure that that's set. Make sure that we have the bridging header set as well. If we don't have those right, then Swift won't know what's going on. So we have our header file. We've exposed it to Swift using the bridging header. We've got our .a file. In theory, everything's sort of here. So I'm going to try and build and run, or just build for a moment, this project. Okay, it seems to be linking okay, but we're not actually using it for anything yet. Let's go into our view controller, and we're just going to use this view did load as a bit of a dumping ground for testing out our library today, because we can't be bothered writing any actual iOS UI code. So you can see that auto completion has actually picked up the imported function, hello dev world, and now I can run this thing. Here comes the simulator. If I can work out how to move that. Okay, so that's run. And down here in the console, we can see it's actually printed out the message. So Rust printed to standard output, and that's been forwarded through to the console in Xcode. So this is great. Our we created a universal binary, a libanvil.a. We created a manual header file, anvil.h, and then we were able to actually call our C Rust function from inside our view controller. Very good. Stop that. Yeah, you can do this on a physical device. At the moment you have to disable bitcode, which is annoying, but that's a work in progress. Nope, can't be bothered doing that. Let's have a look at the next module. So now we've got some Rust code actually executing inside the IL simulator, which is pretty cool, but we need to streamline this quite a lot. For a start, the fact that we had to write our own anvil.h was quite bad. It was fairly obvious what the C representation was supposed to be. Void, hello dev world void, because it took no parameters and it had no return type. So we're going to improve on that. We're going to use a tool called cbindgen, which is very popular for reading through your source code in Rust and automatically outputting a header file with all the parameters and return types and so on automatically configured correctly. So you can do this, you can invoke this from the command line just as a cbindgen. The tool is installed via cargo. Or if you want to, you can script this through the build.rs build script, which I'm not going to do. But if you want to be able to just run cargo build from the command line and cbindgen automatically updates itself, then that's one reasonable way to go about it. Yep. Okay, let's go to the actual text. So to make this more interesting, the first thing we're going to do is add a couple of extra kinds of functions to our library, because we're not really getting the benefit out of it. Oops, that's the test one. Let's put it inside the actual library. Okay, there's our hello dev world. Doesn't take anything or return anything. These ones do though. This is a function that adds two integers together and returns them. And this is one that takes a string as an argument and returns the length of the string. Don't worry too much about the string one and all the C-store business. We're going to get onto that a little bit later. I'm also going to say some more about why we're using this cint C long stuff a little bit later, because that's not... if you know some Rust, you realise that this is quite strange. Why aren't we using, you know, i32 or i64? But there's a reason for it. Next thing, let's make sure we've got cbindgen installed. I haven't actually run this for a while. It may actually update for me. There we go. We're going to be doing this video with a new version of cbindgen. So that took a little while. As I did mention, the Rust compiler is a bit slow, but now we can actually run the cbindgen command, choosing the language C and outputting the file into the target directory. So if I have a look at that file, we can see that it has all by itself come up with the hello dev world definition, and also some other definitions for our add numbers function and also our string length function. And you can sort of start to see here where the where we used C long and cint. Those have come across directly to the values, the data types used inside the header file, and that's the main benefit of using these C types from the standard OS raw library, because the C types don't always match directly to the Rust types, because an int could be 32 or 64 bits, for example. So using these ensures that it always stays in sync with the header file, because if it changes, you might have downstream build problems. So we confirmed that's the file we got, and since we've added a couple of new functions, we now have to rebuild our library for the two architectures, and we have to recombine them again into the universal library. As you can see, this is kind of annoying. We're going to be automating this in the next module. And now we can go to our iOS project, and we'll get rid of the header and the .a. And now we can use our new .a file, which we just created with LiPo, and our auto-generated anvil.h. Replace them there, and then they'll be there in the Xcode project. Now in our view-did load, we can do some more. We can do some more Swift, so we can add a couple of numbers together, print out the answer. We can come up with a string and give it to the string length function, and I'll point out, I'll have a bit more to say about it later, but you can see that this is a normal Swift string and we're just passing it straight into the string length function, and that's because Swift support for C libraries is pretty good and pretty magic. It just knows how to express one of its strings as a C string to pass in as a pointer. So having done that, let's run that in the simulator. And as we can see, that's actually working fine. We've got the answer is 40 and the length is 46, which is correct. That is the length of that string. Wonderful. I'm not going to bother doing the unit test example now or adding more functions. This is just stuff that if you haven't done Rust before, you might find interesting. So far things are going pretty well. We've now automated creating our header files, but we still have this sort of annoying dance we have to go through every time we change our Rust code. We have to build it once for the ARM64, once for the simulator, then we have to use LiPo to merge them together, then we have to copy them into the iOS project. Who wants to do that all the time? So what we really want to do is automate this so that when we hit the run button in Xcode, all of this stuff just happens automatically. So that's what we're going to do in this module. And it's going to be quite straightforward. We're just going to add a run script to our build phases, and inside that put in a bit of a bash script that's going to do all of these steps. So I'm going to copy that text, bring up my Xcode project and add this build step. So it's under project, app, build phases, new run script phase. I'm going to click and drag this up before compile sources, because if our Rust is not up to date, our Swift sources won't necessarily compile if we're referring to Rust functions that it doesn't know about yet. Just to be pedantic, I'm going to change that to bin bash and set this up. So this is a script with a few values pre-filled in. I need to make sure that the folder is correct for my Rust project. The iOS one will be correct because that's the name of my group, Anvil. That's where my Rust utilities were installed by RustUp. This is good. And these are the things that it's going to do when it runs. It's going to use cbindgen to create the anvil.h file based on whatever is in my library at the time. It's going to do the build for ARM64, it's going to do the build for Simulator, it's going to combine them, and then it's going to copy both the anvil.h and the libanvil.a into that group, overwriting whatever was already there. So that should basically just work. Let's see if that's true. So at the moment we've got hello dev world being called and writing this to the console. Let's change that text inside the library, version 2. So all I've done is edited and saved my lib.rs file. I'm not going to do anything at the command line. I'll come into Xcode, hit the play button, and hopefully it's run that build script in the background. And there we have it. It's automatically updated everything for us, and now we can just edit our Rust code, hit run in Xcode, and everything is already up to date. But let's have a look at this exercise, because I think it's kind of useful. Obviously, if there's a mistake in the Rust code and it doesn't build, then that means that iOS can't build either, or it shouldn't anyway. So let's try this first one that's suggested. Leave the exclamation mark out of the print line macro. Sure, let's do that. Let's delete that guy, save it, and try to run this in Xcode. Excellent, we've got an error. Could not compile Anvil. Right, let's click on that. So this is quite nice. It's actually brought the Rust C compiler error straight into the Xcode log, so we can get all the help that we need. Help use this to invoke the macro. Okay, sure. Let's put that back. Let's try this other one though. Adding an extra brace here. This is sort of really breaks the syntax in a way that just leaving out the exclamation mark doesn't. So I'll try to run this in Xcode, and now we've got a different error. Command phase script execution failed with a non-zero exit code, and we've just got an error, Lex error. Couldn't generate bindings. So this is the main clue here. Couldn't generate bindings, and that is an error that's coming from cbindgen, as we actually haven't got to the Rust compiler yet. And when cbindgen hits a syntax error, it just throws Lex error. It doesn't tell us anything nice like the Rust compiler does. So I had this as a bit of an exercise to see if you could sort of improve this. I'm just going to tell you that you can fix this. All you have to do is compile your code first and then generate your bindings, which means that the Rust compiler gets a chance to tell you what's gone wrong. And now we're seeing the Rust errors come up here straight in our left hand side bar, which is wonderful. Unexpected close delimiter. Okay, great. So now I can go and fix that problem, compile that, and it will do the C bindings after compiling the Rust code, and everything is wonderful. Module 5, primitives, structs, enums. I don't have much special to say about this. What we've done so far is get our Rust library compiled for the iOS targets, and brought into our Xcode project as a static library. And now we've finally automated the whole thing. So we automatically get the bindings we need. We automatically build it when we have changes to our code. So now we can start to focus on how do we actually call more interesting functions? How do we shuttle data between Swift and Rust? If we have a look at the text for this one, we're going to start out by looking at some of the primitives. So, as we know, in Rust, we have these types of numbers, I8, I16, I32, U8, U16, U32, usize, etc. But we haven't been using those inside our C headers. We've been using the ones here inside standard OS raw. So, as I was sort of saying, we need to use the types defined by C to make sure that the widths are right. Otherwise, if we were using, I32, it might come out differently if we were compiling on a 32-bit platform versus a 64-bit platform. Whereas using these means that we can handle any inconsistencies directly in Rust. So if you need to, have a look at this page to see what types are available: signed chars, unsigned chars, and so on and so forth. If you sort of click on them, it will tell you how they're defined. Wonderful. So let's get on with adding a struct, because that's more exciting. Let's include C float because we weren't using that before, and add not only a struct but also a couple of functions to work with the struct. So if you want to use a struct over FFI, you have to make sure that it's packed in the way that a C ABI would expect. So you have to use wrapper C. There's a few things that you can use for wrapper with enums in particular, but it's important to use C here. We've defined a point which has two float values and a couple of functions here that actually work with points. One that returns one that accepts one as an argument. So give me a point will return a point, x 3.14, y 12.0, and this magnitude function will accept a point and return a scalar float, sort of doing the hypotenuse calculation there. So we can build that in Swift because we've got our build script in place, and use that inside our view controller with this code that's supplied here. Just going to comment out this earlier stuff to make it a bit clearer. So we're going to ask for that point. We're going to calculate its magnitude and print some stuff out. We're also going to create a point of our own, because defining the point struct and making it public and wrapper C means that it's fully exposed to Swift. So we can create our own points from Swift and then ask for the magnitude of those. So those are all compile errors because it hasn't updated the Rust code, but I'll hit run and there we go, it's working. So that's the sort of hypotenuse length for the point that Rust gave us, and this is the one that we created ourselves, another 1 and 2. So I had a suggestion here. Place a breakpoint in this code and step through in the debugger. You should be able to inspect the values of P and another like any struct. Well, sure, let's do that. Alright, let's move me out of the way. Get that there. So let's step over that, and now we have P. It's actually a point type. We can see the values. Another is another point type. We can see the values. So you can see that this is actually understood as a real struct from Swift's point of view, even though it was originally designed as a wrapper C struct on the Rust code. And the other thing that's important to note here is that all these values that we're working with are on the stack. They're being returned and provided directly as arguments and return values. So if you get a point from Rust and you change a value, you're working with your own local copy. It doesn't affect anything anywhere else because you have your own memory for it. Now, let's have a look at an enum, which is Similar, but different. We're going to have a traffic light, which can be red, yellow, or green, and a very simple test function. It's just what color, and it's going to return a traffic light value, and it's going to be green because it is, that's all. And we can sort of check this from Swift. What color is it? If it's green, we go. If it's anything else, we stop, because we want to stop on a yellow light, don't we? Alright, and it says we go. Fantastic. So the interesting thing to see here is that we have had the enum values come through as constants, green, which is not necessarily what you want. So there are a few ways you can configure cbindgen to output these values. You can use qualified names, you can use capital names, and so on to maybe make these less ambiguous, particularly if you've got a lot of values, types and enums coming through from your Rust code. So there's a link in the document here to the user guide. You can mess around with the rename variants to make your enum cases have maybe better names in your header file, which means that they might be easier to use from Swift. In this next module, we're going to look at strings, string types, and a little bit about heap allocation. So the first thing I want to talk about is the fact that we have this unsafe thing in our code. This was introduced in an earlier module. Probably more people who are watching this video are already familiar with what unsafe means, but in case you don't, any Rust code that does something which the compiler cannot prove is safe has to be called out as unsafe by using either an unsafe block or by marking your entire function as unsafe. This function is doubly unsafe because it is dereferencing a raw pointer that has been provided by C. We don't know that it's in a valid memory region. We don't know that there's going to be a null terminated string at the other end of it. And the second reason it's unsafe is because we don't know that it's going to be a valid UTF-8 string. All Rust strings are guaranteed to be valid UTF-8, and it's an error if they're not. So we are promising to Rust when we pass in this pointer that it's going to be a valid null terminated pointer to UTF-8 data. And because nothing about this can be assured, we have to put it inside an unsafe block. So Rust has two main types of string. There's the capital S string, which is pretty similar to a Swift string. It's UTF-8 text stored on the heap. It can be mutated, it can be dynamically sized, and so on. Then we have a string slice, ampersand str, which is a read-only view into some string data. It might have come from a capital S string, or it might be sort of hard-baked into your binary or some other place. Both of these are different from the kinds of strings that we get from C, or from FFI, which is a const star C char, which is a pointer to a bucket of bytes, basically. So we don't know that anything about it is necessarily valid. We sort of have to be careful with it. And to translate between that type and normal Rust types, we have to use the C-stir and C-string helpers. So with that explained, let's have a look at the actual text. What we want to do, just to make this a bit more fun, is add a calculation for the Levenshtein distance between two strings. If you haven't come across this before, it's a nifty algorithm that basically gives you a number telling you the edit distance, how different two strings are from each other. And you can sort of see here, cat versus cat gives you a score of 0, cat car distance of 1, cat dog 3, cat kta 2. CTA, I guess I could say. So that would be fun, but you know, there's the actual algorithm for calculating that is not straightforward, but thankfully someone's actually written a Levenshtein crate, which we're going to use. So what we're going to do here is use the Levenshtein crate to get access to a Rust function, and then we're going to write a wrapper function in our lib.rs that accepts the strings as the C types and converts them to Rust strings and calls the Rust function, gets the answer, and then sends it back through the library layer. So first step, let's add this dependency to our cargo.toml. Done. So here, Levenstein function is going to take string slices as its arguments, which is not what we're getting from C. So this is our library function. We take two const char arguments and we return a cu long, just a number to say what it is. And we're actually getting some compile errors here. This was sort of an intentional thing because I wanted to point out this this unsafety, because we've got sort of three things we can do. If we don't get valid UTF-8, we could maybe return an error code, we could choose to crash, or we could use a different function like the lossy string function to just strip out anything that doesn't look like valid text. In this case, we're going to take the unsafe option and just unwrap our results, which means that we're basically guaranteeing that C is always going to provide valid UTF-8 data, and if it doesn't, we agree to crash. That's just what we're going to do. We're going to panic. Alright, and that's what this version here is with the unwraps in place. So looking at this, we can see that we're using cstr, which we imported earlier. The from pointer function will take one of these const char guys, and then we'll convert it to a string slice, unwrap the result, and we'll do that twice, once for each of the arguments, and then we can pass both of those into the Levenstein function, which will calculate the distance for us, which is a number, and then we cast that number back to cu long to return that to C as an unsigned long. Once we've done that, we can use it from Swift, of course. So I'm going to comment out the stuff that we've done so far. 2 words, agreeable, affable. Let's calculate the Levenstein distance between those and print it out. I have to build and run before it knows about the function. And there we go. Distance is 4. How about that? So that was one example, and the specific example here was this is how you send a string from Swift to Rust. Now let's look at the opposite case. How about Swift calls into Rust, but Rust is actually going to return a string to Swift? That's what we're going to add next. So let's add another import first. We've been using cstr, but we're also going to need cstring to do this one. And now we're going to create a function, and it's going to be a function called give me letter A. We'll pass in a count, a number, and we're going to return a string, star mute C char, and it has to be mutable because we're going to free it later. What this function is going to do is basically give us that many copies of the letter A, which is something that Rust will let us do quite easily. Let's copy this into our source code. So fully in using normal Rust string code, we're going to take the letter A and repeat it with the supplied count. Then we're going to convert our string into a C string, that helper that we imported a moment ago, and then we're going to provide a pointer to C using into raw. Now into raw is a function that means Rust gives up caring about the memory momentarily. It's allocated it on the heap, but we're sort of trusting the C side to look after it from now. It's up to Swift what it does with that memory from now on. So we can use this from Swift by calling give me letter A5 and printing it out. But what we get from the function directly is not usable as a string in Swift. We have to use this special string initializer with cstring 5a cstr. So let's add that to our view controller. Do I actually need to do that? I don't think I do. I think I can just do that. Yeah, there we go. That's even better. Alright, so we've initialized our Swift string with the C string. We can print it out. And you should also notice here that this is actually coming in as an optional pointer or an implicitly unwrapped pointer. It could be null. And if it's null, we'll just say return string was null. But it's not going to be null. So we'll run that. There we go, 5 of letter A. So that's worked, but there's a loose end here. We created that heap memory allocation to store the 5 letter A's, return the pointer to Swift using into raw, but now that's a memory leak because nothing ever happened to it after that. It's just sort of sitting there. So what we need to do is add a free function to our Rust library, which we can then pass the pointer back in. And then we'll create our C string from raw, which takes ownership of that memory again. And then we could actually just end the function there and it would drop. But to be explicit about what we're doing, we'll call the drop function. And that means that the heap allocation for that memory will now be deallocated. So that just means that we need to free our string from Swift after we've finished initializing our own Swift string with it. So if I stop and run that, it should do exactly the same thing again and not crash or anything. But this time it's actually cleaning up the memory. So that's good. Unicode support. What is the Levenstein distance between these emoji? Yeah, sure, why not? Let's do that. Just because it's kind of silly. Give me doggy. Come here, doggy. No, I don't want to look up the definition. Cat and dog emoji. Edit distance is 1 because they're 1 character. Of course, they're more than 1 byte, but they're 1 character. Fantastic. In this last module, we're going to have a look at callbacks from Swift. In other words, function pointers. So we're going to be adding this function. This is what it's going to look like at the C level. And if you've done a lot of C programming, you'd be familiar with this idea of C function pointers. So this is a function, add numbers CB, that takes 3 arguments. 2 of them are integers, and the third one is a pointer to a function. And the name of this parameter or argument is callback. It's a function that takes an int as a parameter and returns nothing, returns void. So we're going to use this. We're going to provide this function from our Rust library, and we're going to call it from Swift. So this callback is actually going to be represented by a Swift closure. Let's go to the text. So from Swift, this is how we actually want to use it. We're going to call add numbers CB and pass in 2 numbers. And then as the third argument, if you're familiar with the Swift syntax where you can sort of put your closure at the end if it's the third argument, we're going to get the answer as a callback rather than as a return value. And I've put these print statements on either end so that we can see the order that things get executed, because if you provide a closure, it doesn't necessarily get executed immediately. It might come later. So I'm going to comment out what we've done so far at this, but we haven't actually done the Rust code yet, so that's not going to compile. Let's add our Rust code to our Rust project. Now I want to point out here that I'm using a callback parameter of type fn with lowercase f. If you're writing Rust code normally, you would probably see a capital F, because that means you can use closures with captured context. When we're using a lowercase f, that means we're talking literally about a function pointer. There is no context. There are no closed values. So what this function is going to do is add the 2 numbers together and then invoke our callback with an integer answer. Easy. And then it will do it while it's actually running. So we will see that we get the first print statement, adding numbers with callback. Then while it's executing add numbers CB, we will get this closure invoked. The answer is 9. Then the function returns, and then we print out this other string, finished adding numbers. But, we don't necessarily have to call that code synchronously. So we're going to look at another example here, which is a countdown timer. We're going to call this function from Swift called countdown. And this time we expect the closure to be called multiple times. And each time we're going to be given a value called timer. So I'm going to tell you now that what this timer is going to do is start at the number 15 and start counting downwards. And once per second, our closure is going to be invoked until we get down to 0. So while the number is higher than 0, we'll print out how many seconds are left. And then once we finally get to 0, we have liftoff. So we can do this from Rust, and we're going to do it using a thread. Cool thing about running Rust on iOS is that we can create threads as normal from Rust, and they will just work. They get to run in the background of our app whenever the app is in the foreground. So that's really convenient and flexible. And I'm going to add those imports and implement our countdown function. So let's have a look at this guy. We're going to be passed in a closure, and well, the Swift closure, which we see as a function pointer, and what we're going to do is spawn a thread, and it's going to spend most of its time sleeping. We'll start at the number 15, sleep for 1 second, and invoke the callback with that number 15, and then we'll decrease to 14, 13, 12, and once per second this will get called. So that's all we need to do. From Xcode, we'll compile and run that code and see what happens in the console. 15, 14, 13. Oops. How do you move this? There we go. And it finished. Next, let's do another test. I'm going to run this, and while it's running, I'm going to press the virtual home button on the simulator to put the app into the background. So that started counting down. I'll hit Command-Shift-H. That countdown is paused because our app's in the background. Now I'm going to go back into the app. And we can see that the countdown picked up where it left off, basically. So you can see that this is the behavior that you can expect from Rust threads that you create when they're running in iOS. And that will finish as normal. Excellent. So this is kind of cool. We can now call functions into Rust from Swift and provide a closure which either gets executed synchronously or maybe asynchronously, maybe multiple times. But what if we wanted to return a value from our closure? Turns out that works totally fine too. And to demonstrate this, we're going to introduce a new enum called countdown command and give Swift the chance to cancel the countdown partway through. So I'm going to replace the countdown function in Rust with this more sophisticated version. And we can see here in our definition that the function that we're provided from the Swift side still accepts an integer as its argument, but it returns a countdown command, one instance of this particular enum, which could be either continue or abort. So once per second we're calling Swift, and Swift is going to have to tell us whether we're going to continue or whether we're going to abort. So as before, we sleep for 1 second, starting at 15, but then we take the callback return value and match on it. If it's continue, we continue to the next iteration of the loop and sleep again. If it's abort, we break and we just don't do this anymore. So we can change our Swift code to take advantage of this and return the enum value, which will come through the C header. So what's going to happen is the time is going to get down to 7, and we're going to say actually we're going to return the abort value. Now let's run that Swift code and see what it does. "15, 14, 13. Cool. So the timer got to 7, and instead of printing it out, we printed aborting and returned abort, and the Rust thread terminated. We already did that backgrounding. There was one more exercise which I included here, which was non-static closures. You'll find out that if you try to use things like self inside these closures, that you can't pass it then as a function pointer to Rust, which is an interesting problem which I'm not going to go into today. You can work around it. There are ways and means, but it's sort of outside the scope of this workshop. So to finish up, as I said, this was mostly a workshop intended for people who actually hadn't used Rust much before, but in case you weren't aware, these are the main resources which you should have a look at for learning Rust. There's the book, which you can access through RustUp if you used RustUp to install Rust. You can access the standard library reference the same way, and the Rust Users Forum is also a really good way to learn more and get help with your programming problems. So that's the end of the workshop. Hopefully you've now got a bit of a foundation in how to set up an Xcode project and bring in some Rust code. Thanks for listening.